Welcome to the Chapter 6 webinar for the CPCI 5th Edition Design Manual. This is the 6th webinar in a series of webinars to introduce the latest edition of the CPCI Design Manual. My name is Ariane Sabourin. I am the Marketing Manager for CPCI. We are delighted that you have taken the time to join us for today's webinar, which highlights the new additions to Chapter 6 related considerations. Our presenter today is Robert Burak, President of CPCI and the editor for Chapter 6. Today's webinar will be approximately 30 minutes in length. Participants will be muted from the discussion, but you are welcome to type in any questions in the Q&A box that's on your screen. These will be answered at the end of the presentation. I would also like to mention that the attendees will receive a certificate of completion after the webinar, which can be used for professional development hours. And we are also recording today's session and we'll make it available on CPCI's website. Before we start the presentation, CPCI would like to acknowledge the support of our sponsors of the Design Manual webinar series. Thank you to the following companies: BASF, JVI Inc., MCM Industrial Consultants, and Ultraspan. It is this type of support from our members that assures CPCI can continue to develop and deliver high-quality programs and services such as this, and to build on our body of knowledge for the architecture, engineering, and construction industry. So without further ado, I will now turn it over to Robert for the presentation. Thank you.
Thank you, Ariane, and thank you to everyone who has taken the time out of their schedules today to join us for this update on Chapter 6. As a brief introduction, engineered precast structures must consider, first and foremost, the analysis and design of elements, structures, and connections. These guidelines are covered in previous chapters of the design manual and have been highlighted in previous webinars. In a balanced design, however, designers must also consider other factors shown here and are also discussed in this chapter. These include the building envelope, particularly considerations for rain penetration, vapor diffusion, air leakage, and thermal resistance. This is covered in section 6.1. Acoustical considerations such as airborne sound transmission, typically defined by the sound transmission class STC, and new to the NBC or National Building Code, apparent sound transmission class or ASTC. This is covered in section 6.2. Fire resistance and the design for heat transmission for floors, roofs, walls, and ceilings. This is covered in section 6.3. Acceptable vibration limits, particularly for sensitive occupancies such as office, residential, and sporting facilities. This is covered in section 6.4. Sustainable design, including environmental impacts and life cycle assessment of materials and assemblies from cradle to cradle. This is covered in section 6.5. And mechanical, electrical, and other subsystems coordination, and this is covered in section 6.6. The highlighted sections on this slide are the sections that have the most substantive changes or additions from the previous edition, and today we'll review the latest additions or changes to these sections. An important new reference document in this chapter in section 6.1 is shown here. This is the recently published CPCI Architectural Precast Concrete Walls Best Practice Guide, authored by M.E. Hackborn of M.E. Hackborn Engineering. The purpose of this best practice guide is to summarize the most current information and best practices in architectural precast, and to provide designers with an understanding of this construction system by illustrating recommended design details and site practices. In the next few slides, I'll highlight the sections of this new best practice manual dealing with this part of the CPCI design manual, particularly on building science considerations. Following this webinar, you are encouraged to download the full document on our website at cpci.ca under our resources section of the website. Chapter 4 of this new best practice guide is entitled Performance. It discusses how architectural precast concrete wall assemblies are designed to provide effective control of air infiltration and moisture penetration through the building envelope, while at the same time providing the aesthetic appeal desired by the architect and the owner. It also discusses how the building envelope acts as the environmental separator between spaces of different environmental characteristics, and how well-designed building envelope assemblies use proven and tested building science concepts to ensure performance. The principles are consistent with the well-documented Canadian Building Digest CBD 48, Requirements for Exterior Walls by Neil Hutchian, which outlined these basic performance requirements for exterior walls. Although originally published in 1963, it has set the foundation for building envelope design principles for decades. It details the following performance requirements: control of heat flow, control of airflow, water vapor transmission, rain and snow penetration, control of light, solar, and other radiation, noise, fire, strength and rigidity, durability, aesthetic appeal, and economy. Chapter 5 of this new reference guide discusses how one of the critical links to a weatherproof building envelope is the joint design and the selection and use of sealants and membranes to ensure that continuity between similar and dissimilar building materials exists. The design and execution of these joints is extremely important and must be accomplished in both a constructible and economical manner. Selecting the right product, appropriate joint design, proper surface preparation, and correct application technique will ensure the joint and sealant provide the desired performance, design service life, and pleasing long-term aesthetics. Joints are required to accommodate changes in wall panel sizes and structural dimensions caused by changes in temperature, moisture content, and applied loads, while at the same time prevent water, air, and vapor penetration through the building envelope. Design criteria for joints include exterior exposure, considering the bulk or the building orientation and climatic conditions, structural requirements, considering the amount of movement to be accommodated, for example, primary structure creep, interstory drift, building sway from seismic considerations, and thermal expansion and contraction effects of the panels in the structure, interior climate of the building, architectural appearance, function of the building, construction tolerances, and economics. There are a number of helpful details that are included in this section. They illustrate architectural precast concrete assemblies in many different configurations and how they interface with other assemblies. Each plan or section detail displays the various components normally associated with typical Canadian and North American construction. The details are divided into two main sets, one for single-wide precast concrete wall panels and one for double-wide insulated wall panels. For each detail, a description is provided that indicates the material providing the major building envelope performance characteristics. Precipitation management is indicated by a bold blue line. The air barrier is indicated by a bold green line. Heat flow is indicated by varying width yellow line and the width representing the relative thermal performance at that point. Finally, vapor management is indicated by a bold purple line. The key to all these color-coded lines is that you can visually check for continuity in each of the performance characteristics. This is true for total precast systems and also when precast interfaces with other materials such as clay brick shown here. Another new and important reference document in Chapter 6 is High-Performing Precast Concrete Building Enclosures, Rain Control, authored by Dr. John Straub of RDH Building Science. The Rain Control Guide, originally published in 2013 and updated in 2016, reviews the important requirements for high-performing enclosures as they apply to precast concrete, with special emphasis on the control of rainwater penetration. Precast concrete enclosure walls stand apart from most rain screen walls in several key respects: how they control rain penetration, how they provide air tightness, and their sequence of construction. Both conventional and insulated panels provide better resistance to rain penetration and air leakage if designed as perfect barrier drained joint systems. The precast concrete is considered as impermeable, and any water leakage is controlled at the joints. The concept of a drain joint system for a precast wall assembly is demonstrated here in this isometric projection. The system is characterized as a two-stage joint where a combination of backer rod and sealant is applied from the outside, creating a drainage space in the vertical and horizontal joint of the system, which is drained at the front. In general, the inner seal should be held back at least 25 millimeters or 1 inch behind the backer rod of the outer seal to create a well-ventilated air gap. This requires the installation of tooled sealant on a backer rod installed about 75 millimeters or 3 inches behind the outer face. Weep holes with a minimum dimension of 12 millimeters or 1/2 inch to facilitate drainage are almost always provided in the vertical joints. A bead of sealant is tied to the interior vertical sealant bead with an outward slope and a drop in height from the horizontal joint of at least 100 millimeters or 4 inches, thereby encouraging outward flow of water and resisting the entry of wind-driven rain. Some designers feel the need to design precast wall systems with an air gap behind the wall like a typical rain screen. This is common and necessary to other systems such as masonry wall assemblies. However, for precast wall assemblies, this is not necessary and also very risky. As excerpted here from the reference guide, An air gap behind a conventional precast wall can allow cold weather condensation to form via internal convection loops. The condensed water can then leak to the inside of the building. Also, during assembly and construction, it is difficult, if not impossible, to seal perfectly around structural supports and properly drain and flash the proposed air gap. Shown here are two drawings excerpted from the rain control manual, courtesy of RDH Building Science. The image on the left demonstrates a perfect barrier drain joint system in a double-wide insulated precast concrete panel system. And the one on the right shows the same with a conventional architectural precast panel. Both figures also demonstrate the type of detailing at a floor intersection that can provide high-performance continuity of the water, air, and thermal control. The joints are fully drained and vented. These types of two-stage joints have a history of successful construction and performance, but it's also important that proper inspection and verification during construction be provided, and that periodic inspection and maintenance during its service life be conducted so that the joint will perform over its service life. Another new and important reference document in this chapter is a guide entitled Meeting and Exceeding Building Code Thermal Performance Requirements, also by RDH Building Science. Section 6.1.4 of the CPCI Design Manual includes 3 RSI calculation examples. Example 6.1 is for a double-wide insulated wall panel, 6.2 is for a hollow-core slab floor system, and example 6.3 is for a double-T roof system. All the design manual examples are limited to component clear wall calculations by simply adding the R value of each component in the assembly. This new guide shown here, however, is more comprehensive and summarizes various compliance paths for meeting today's model energy codes. It provides specific guidance on the impacts of floor slab intersections and anchors in the calculation of what is called a whole wall R value. It also includes advice and guidance on the effective window wall ratio. Although today's jurisdictional energy codes vary in their approach and their requirements for compliance, it is anticipated that most will eventually transition to whole wall R value requirements that include the calculation for thermal bridging of all major components that intersect the wall. A new and innovative resource from CPCI that supports this part of the design manual and this best practice guide is an online calculator to assist in the calculation of clear wall and whole wall R value. Based on the inputs by the user, it compares the results to the code requirements of either ASHRAE 90.1, either 2010 and 2013, the National Energy Code, NECB, either 2011 or 2015, and the Ontario Building Code, 2017. All of these codes are included due to the provincial adoption of varying code requirements. This calculator will be available on the CPCI website soon, and we will be conducting demonstrations of this new software regionally this fall. Section 6.2 of the design manual covers acoustical properties for precast concrete assemblies. The simplest approach to sound transmission between adjacent rooms and buildings considers only the sound transmission through the wall or floor that separates adjacent spaces. This is shown on the top left. And for many decades, our codes have considered only the ratings for the individual separating assembly, the sound transmission class, or STC. This approach assumes that sound is transmitted only through the obvious separating assembly, that is, the separating wall assembly when the rooms are side by side, or the floor ceiling assembly when the rooms are one above the other. New to the design manual and new to the National Building Code in 2015 is apparent sound transmission, or ASTC, which we cover in the design manual in section 6.2.14. In reality, there are many paths for sound transmission between adjacent rooms, including direct transmission through the separating assembly and indirect structure-borne paths. This is shown in the top right. The structure-borne paths usually will significantly affect the overall sound transmission. The apparent transmission loss, or ATL, between adjacent rooms includes the combination of direct airborne transmission through the separating assembly and structure-borne flanking transmission via 3 pairs of wall and floor surfaces that are connected at each of the 4 edges of the separating assembly. This is shown in the bottom diagram. Excerpted here is a simplified ASTC example from the design manual. This example is for 2 rooms above each other. The floor ceiling is a 203 millimeter or 8-inch thick hollow core assembly, and the walls are 150 millimeters or 6-inch thick concrete. The separating junctions and acoustical parameters, the dimensions and masses, are described and summarized here. This is a visual of the 4 junctions that I previously mentioned for the design example. This diagram describes the process for the ASTC calculation. Steps 1 through 2C are determined through laboratory analysis, which CPCI has conducted at the National Research Council laboratories in Ottawa. Steps 3 through 5 are calculations to arrive at the final ASTC for the assembly. They include first, the direct transmission STC through the separating floor, and then they include the STC for the flanking pass, which are calculated for each junction. The equations for these are found in ISO 15712, entitled Estimation of Acoustic Performance of Buildings from the Performance of Elements. So as you run through the example, this is the resultant STC for the separating floor. This is the STC for junction 1. This is the STC for junction 2, then for junction 3, and then for junction 4. Then the combined STC for all the junctions is calculated, and finally the ASTC due to direct plus total flanking is shown here. In this example, the ASTC is calculated as 50. The minimum ASTC requirement in the 2015 National Building Code is 47. The National Research Council has developed an online software to simplify the calculations for design professionals. You can access the software called SoundPass through the NRC website by the link above. Several different types of assemblies are included, and more continue to be added as more testing is completed by the National Research Council on different assemblies. For example, in early 2018, CPCI also commissioned the NRC to publish this document, which summarizes ASTC calculations for several hollow core and concrete masonry assemblies. These are now included in that new software. Shown here are the tabulated summaries for rooms side by side on the table 1 on the left, and summaries for rooms above each other, table 2 on the right. In both cases, 3 different masses of hollow core are modeled, and floor toppings are added to 4 of the scenarios. Links to these new architectural precast and acoustical resources that are now referenced in the 5th edition design manual and that we have covered briefly today can be found here in the resources section of the CPCI website. The chapter also includes a section 6.3 on fire resistance. Aside from editorial changes, this section is largely unchanged technically from the previous edition. However, for new users to the manual, it describes the methodology for calculating capacities and the required reinforcement for fire-resistant hollow core and double T elements. Section 6.4 deals with vibration of structures. As with the previous section, this is largely unchanged except for editorial corrections. Vibration calculation examples in this section include example 6.1 on hollow core, walking vibration, and example 6.11 on stadium seating for a lively concert or sporting event. Section 6.5 of the design manual includes information on sustainable design and construction. New to this section is a summary of the life cycle assessment that was conducted on behalf of CPCI and our partners at PCI and NPCA. It was conducted by the Athena Sustainable Materials Institute in Morrison Hershfield. The study was published in 2012. In order to better understand precast concrete's environmental performance in the context of building construction, use, and end of life, a life cycle assessment was conducted for a typical precast commercial building with 5 variations of building envelope and in 2 Canadian locations. The LCA study is entitled Life Cycle Assessment of Precast Concrete Commercial Buildings. It's a cradle-to-grave LCA of precast concrete commercial applications in both Toronto and Vancouver. The study considers the impacts at each stage of a product's life cycle, from the time natural resources are extracted and processed through each subsequent stage of manufacturing, transportation, product use, recycling, and ultimately disposal. Environmental flows include emissions to air, land, and water, as well as the consumption of energy and material resources. Inventory analysis, or life cycle inventory, LCI, is the first step towards environmental impact assessment. The inventory analysis for this study involved collecting data for precast concrete products within a plant boundary, as shown here in figure 6.5.4 from the design manual. The buildings were modeled with Energy Plus whole building energy simulation software that was developed by the US Department of Energy. It simulates the complex interactions between climate, internal gains from lights, people and equipment, building form and fabric, HVAC systems, and renewable energy systems. Annual energy use by end use, as determined by the energy simulation software, is presented in figure 6.5.6 for Vancouver and figure 6.5.7 for Toronto. The results for both locations show that precast envelope options have the lowest overall site energy use by approximately 1% when compared to curtain wall or brick and steel stud. The LCI and LCIA modeling software that was used was SEMA Pro version 7.3.0 from 2011. Each building constituent element, material, product, or process is modeled independently from cradle to grave. These elements are then combined to comprise a complete building subassembly. Finally, each of these building subassemblies is then combined to model the complete building structure and envelope as constructed on site. The buildings are modeled for 60 and 73-year service lives. 73 years is the median life for large commercial buildings supported by the U.S. Department of Energy in 2008. However, when performing an LCA of buildings in Canada, it is common practice to assume a 60-year life. For example, the default life in the Athena Eco calculator is 60 years. The model also considers the environmental impact associated with maintenance for each material and assembly. The primary source of information used for this was the Athena report, Maintenance, Repair, and Replacement Effects for Envelope Materials from 2002. It describes the maintenance stages for each assembly, material and energy usage, the rate at which each activity occurs, and construction waste factors. Again, this reference document and other resources on sustainability can be found on our CPCI website in the resources section. Section 6.6 of this chapter deals with mechanical, electrical, and other subsystem coordination. Precast integration with lighting, mechanical, plumbing, and other services is very important. This section shows some methods that can economically satisfy mechanical and electrical requirements and describes standard methods of providing for the installation of other subsystems. This section is largely unchanged in the 5th edition, except for editorial corrections. So this completes the highlights of the changes and additions to Chapter 6. We'd like to acknowledge other significant contributions to this chapter. Two sections, 6.3 and 6.4, were edited by these subject matter experts. Section 6.3 on fire resistance by Stephen Scalco, PE and Associates, LLC, and Section 6.4, vibrations in concrete structures by Dr. Mike Lau of Dillon Consulting Limited. We also had some peer reviewers from the CPCI Technical Committee, Bill LeBlanc, a PN from Armtech, and Sonia Sari, PN from Core Slab Structures Incorporated.
Great. Thank you for this very informative presentation, Robert. Please mark your calendars for the upcoming webinar presentations. So the next presentation for Chapter 7 on product information and capacity will be held on Wednesday, October 10th at 1 p.m. Eastern. And our last webinar for Chapter 8 on general design information will be held on October 24th at 1 p.m. Eastern. You can register for these webinars online at cpci.ca under the resource section, and there is a page there called Design Manual. I would also like to remind you that if you've missed any of the previous webinars, they are available for streaming on the CPCI website on that same Design Manual webpage. So once again, we would like to thank our Design Manual webinar series sponsors for their support of the webinar series: BASF, JVI Inc., MCM Industrial Consultants, and Ultraspan. And at this time, I would like to open up the seminar for some questions. So if you have any questions, please type them in the Q&A box that appears on your screen. And I will now turn it over to Robert again.
Thanks, Ariane. I'll just click on the Q&A box here. I see 4 questions right now. The first one, I'll read it out loud. I'm an Ontario architect, and I'm wondering if your requirements for drainage of a precast wall using 2-stage joints without a rain screen behind the wall meets the pro-indemnity insurance requirements. So I'd say this is a really good question, and we often receive this question. So the pro-indemnity insurance coverage does provide specific exclusions for a number of different assemblies, and this does include precast concrete. So for precast concrete, they specifically do call out walls designed and constructed as drain systems utilizing 2-stage drainage joints. or two-stage drain joints. So yes, you would be covered. This exception was recently added actually to address this kind of question, which is quite common because there were some problems with rain leakage and condensation caused by designers attempting to create drainage areas and gaps behind the precast. Okay, the next question is, I saw on one of your slides the use of ceramic fiber felt in the joints between the panels. Is this a requirement in all cases? So I'd say that the joints between wall panels are similar to unprotected openings, like windows and doors. And in the National Building Code, there's a calculation for allowable percentage area of unprotected openings. So typically, when you do that calculation, in many cases, joints don't need to be fire protected. However, in other cases, there might be a reason to fire protect them. And that chart or that table that you saw in that slide is if I recall, table 635 of the chapter. And it refers you to solutions using ceramic fiber felt. Now, quite often, a fire consultant will approve a fire-resistant caulking in its place as well, too. Okay, the next question. I noticed on one of your slides on sound transmission that there were examples of hollowcore ASTC results for hollowcore with different masses. Does it matter what mass we use to meet the new requirements for the building code? So that's a good question, too. Because the ASTC is a new provision in the building codes, assemblies of all materials needed to be verified so that design examples could be calculated. Specifically with hollowcore, because it's not homogeneous, it has the cores in it. NRC did require us to do some testing. So we tested 3 different masses of hollowcore. We tested masses of 275 kilograms per square meter, 300 kilograms per square meter, and 338 kilograms per square meter. And what we found, or what they found, was that it did act homogeneous. So all the design examples that are in the reports that we have and that are also on our website all meet the requirements. But essentially, the reports state that any assembly with hollowcore over 275 kilograms per square meter will meet their ASTC requirements. Okay, the final questions. I found the LCA information interesting. Has the precast industry done any other work on sustainability or sustainable practices? Yeah, since the LCA was published in 2012, we've added some interesting programs. One is a software that we had developed by the Athena Sustainable Materials Institute. It calculates the environmental impact of precast products from cradle to gate. And this program has also since been adopted by our US affiliates of PCI and NBCC, and we have that program is now called the North American Precast Concrete Sustainable Plant Program. If you go on our website and you go to sustainableprecast.ca, you'll be able to download a quarterly report that we publish that is the results of the reporting from our plants that voluntarily participate in the program. You'll also see at sustainableprecast.ca our environmental product declarations, which we recently published as well too. So I think those are all the questions I see. Ariane?
So that concludes the Q&A session and the presentation for today. Thank you again for joining us, and thank you to our presenter, Robert. We hope that you enjoyed the webinar presentation today. Also, if you have any additional questions for CPCI, you can contact us at any time at info@cpci.ca.